For the remainder of Chapter 8, we're going to talk about trends in different atomic properties. We're going to talk about 4 properties in particular: atomic size, ionization energy, electron affinity, and metallic behavior. Some of the actual definitions, actual scientific definitions of these properties are really complex, so I've provided these quick and dirty definitions to make it a little bit easier for you to remember which term belongs with which. So atomic size isn't that complicated to imagine. It's essentially how large the atom is. And we'll talk about the trends on the periodic table and how you can predict which atoms are going to be smaller or larger than others. Ionization and electron affinity are 2 properties that often get confused with one another. Ionization energy is how much energy it takes if an atom gives away an electron, and electron affinity is how much energy the atom releases when it gains electrons. So ionization relates to the energy when it gives away electrons. Electron affinity relates to when it accepts electrons. And that can be helpful in predicting whether or not an element prefers to make a cation or an anion. And then metallic behavior. How likely is the element to behave like a metal? And we'll talk about some of the properties that make something have metal characteristics or not. So the first property is atomic size. So how big is the definition? And so the real chemical definition is the size is the extent of the contour of the atom. And we usually report that in terms of atomic radius. And so we usually represent atoms as spherical contours where we have the nucleus in the center, and then we have this spherical contour representing the electron cloud. Well, with the electron cloud, there's no wall indicating that the electron cloud stops here. So measuring the width of an atom is actually a little more challenging than you might expect. It's not like a cell where there's a definitive barrier where it ends. And so the way we typically determine the atomic size of an atom is we take 2 identical atoms when they're next to each other and measure the distance between the nuclei, because the nuclei are very easy to see with respect to the electron cloud, which is mostly empty space. And so we can measure the distance between the 2 nuclei, and then we report the size of the atom based on half of that value, which is the atomic radius. And so the atomic radius is often reported in units of picometers or nanometers or angstroms, but remember, all of those are units of distance. And we care about the atomic size because it tells us how close the electrons are to the nucleus, or at least the valence electrons. So the larger the radius is, the further those electrons are from the nucleus, and the less attracted they are. Remember, electrons are held close to the nucleus due to the electrostatic effects. The negatively charged electrons are attracted to that positively charged nucleus. And so what are the patterns for atomic size? The easiest way to remember, in my opinion, is I remember which element is the smallest and which one is the largest, and that's how I remember the trends. So helium is the smallest atom on the periodic table. It has the smallest atomic radius. And francium down here, Fr, which I sometimes affectionately will refer to as Frank, that is the largest atom. It has the largest atomic radius. And so as you're going down a group, the atomic radius or the atomic size is going to increase. That's logical because as you go down a group, you're adding energy levels, and it would make sense that the size of the atom increases as you go down a group. On the other hand, if you're going across a period, so from left to right, the atomic size is actually going to decrease, which might be a little bit counterintuitive. But what ends up happening as you add electrons to the atom, when we get to neon, they end up compacting and becoming closer to the nucleus. So the more electrons you have around it in a given period, the more condensed the atom is going to be. And so as we go across the period, the atomic size is going to decrease. So in any given period or row, the alkali metal will be the largest atom, and the noble gas will be the smallest atom. And so if you take all of these trends, that means that helium is the smallest, and francium is going to be the largest element. And so I like to remember that helium is the smallest, so as you move away from helium, the atoms are only going to get larger. Here's another way of representing it, but in general, what we have here is a graph of the atomic number related to the atomic radius, and these values are represented in picometers. Remember, that's the unit of distance. Pico is 10 to the negative 12 meters. And so as we go across with atomic number, you can see that there are definitive jumps anytime you transition into a new period. So we have period 1 where helium is the smallest, and then we go from helium to lithium, it jumps up, so that's a new period where lithium is larger, and then it gradually gets smaller, and then it jumps up when we go to period 3, and then it gradually, the atomic radius gets smaller. Another jump at period 4, and you can see that there are slight variations in those decreases occasionally, and it usually has to do in the transition element and metalloid area. You don't need to be familiar with these deviations from the trends. Be sure that you know that helium is the smallest, francium is the largest, and the trends that go along with those. Another thing you'll need to be familiar with is the size of the atoms relative to their respective ions. So cations generally are smaller than their parent atom. And so I haven't used the term parent atom before, but if we're looking at sodium, the sodium atom, where it hasn't lost an electron yet, would be the parent atom, and then the sodium ion, after it's lost an electron, would be the corresponding cation. And so we would expect the sodium cation to be smaller than its parent counterpart. And that's true for generally all cations. The parent atom is larger, the cation will be smaller. For anions, it's exactly the opposite. The anion is larger than the parent atom. So a chlorine atom we would expect to be smaller than after chlorine accepts an electron to form the chloride anion. The next property we're going to talk about is ionization energy. And so the real chemical definition is the energy required for the removal of 1 mole of electrons from 1 mole of gaseous atoms or ions. The quick and dirty definition that I gave was how much energy is it going to take for an atom to give away electrons? So ionization energy relates to giving away electrons. And so electrons are attracted to the positively charged nucleus. And if you want to take an electron away from an atom, it's going to require some amount of energy in all cases. Some atoms, it takes less energy. With other atoms, it takes more energy. And that's what the ionization energy relates to. An atom that has a low ionization energy has a tendency to form cations, because if it's a low amount of energy required to give away an electron, the atom is more likely to do it. Essentially, a low ionization energy means it's easy to give away electrons. So metals are atoms with low ionization energies. Atoms with high ionization energies have a tendency to form anions. A high ionization energy means it requires a lot of energy, or it's very difficult for the atom to give away electrons. And so atoms with high ionization energy tend not to give away their electrons. And so elements like nonmetals and noble gases are going to be ones with high ionization energies. We can also talk about successive ionization energies. How much energy does it take to remove just one electron? How much energy does it take to remove a second electron and a third electron, and so on? And it's always going to require the least amount of energy to remove one electron. It will require more energy to remove a second one, and then a subsequent third one, and so on. So the first ionization energy is always going to be the lowest, and so that tends to be the property that we compare. And so the trend that you'll need to be familiar with respect to ionization energy is just the first ionization energy. How much energy does it take to remove one electron? And so the trend is going to be exactly the opposite as it is with atomic size. Remember, with atomic size, helium was the smallest and francium was the largest atom. It's going to be opposite for ionization energy. Francium is going to have the lowest first ionization energy, meaning it's the easiest to remove one electron. Helium is going to have the highest first ionization energy, meaning it's the most difficult atom to remove one electron from. And if you think about the atoms themselves, that makes sense. With francium, it has one valence electron in the 7th energy level. The 7th energy level is the furthest away from the nucleus. So that one lone valence electron is really far away from the nucleus. So pulling that off isn't going to require much energy on francium's part. So it's very likely to give away that electron. With helium, helium only has 2 electrons to begin with, and they're both in the first energy level, so they're very, very close to the nucleus. And so removing an electron from helium, which has a noble gas configuration, it's already very stable, is incredibly difficult. So helium tends not to give away any electrons. And that's why these noble gases are stable. It's very difficult to remove electrons because they have high ionization energies. And so the trends. Down a group, it decreases. So as the atom gets bigger, it gets easier to remove that outer electron. As we go across the period, it becomes more difficult to remove an electron. So the energy, the IE1, is going to increase across a period. So the noble gases will be the most difficult to remove electrons from. And here are some diagrams comparing something like potassium and sodium, which are in the same group. We know that they both have one valence electron and like to give away one electron when they form an ion or participate in reactions. And potassium is going to have a lower first ionization energy than sodium, and it's lower on the periodic table. It's in period 4. And that has to do with the distance that electron is from the nucleus. The one valence electron that potassium has is one energy level further away from the nucleus, so it's less attracted to the nucleus, meaning it requires less energy to sort of pluck that electron off than it would for a sodium atom, which has its valence electron in the third energy level. And then if we're comparing something like sodium and chlorine to each other, sodium has just one valence electron, chlorine's got 7 valence electrons, and the amount of energy it takes to remove one electron from a sodium atom is significantly lower than it takes to remove one electron from a chlorine atom. As you go across a period, the ionization energy increases. As you go down a group, the ionization energy decreases. And remember, that is for the first electron. Here's another diagram representing that information. Here we have atomic number on the x-axis. We have first ionization energy here on the y-axis. And remember, low energy means it's easy to give away electrons. So you're going to find all the metals down here in the low ionization energy region. And then up here, the high energy means it's difficult to remove an electron. And this is where you're going to find the nonmetals who do not like to give away electrons. And so as we go across the period, it increases, and then there's a sharp drop as we move on to a new period. So here we start with lithium in period 2, and we generally see an increase as we go across, and then another sharp drop, another increase, a sharp drop as we move on to the next period. Yes, there are deviations between individual elements, but you're not going to need to be familiar with the deviations between the individual elements, just the general trends down a group and across a period. So let's do an example of ionization energy trends, where we want to put the groups of elements in order of increasing ionization energy. So go from lowest to highest. And so what I would recommend you do when you get your periodic table on the exam is label all of these properties. And for ionization energy, helium has the highest, francium has the lowest. And so if we want to put these elements in order, we need to find them on the periodic table. They're all conveniently right next to each other. And we know that it's the lowest over here and the highest over here, so we can easily put them in order across the period. Carbon would have the lowest ionization energy of this set. Fluorine would have the highest ionization energy of this set. And so we'd put it in order of carbon, nitrogen, oxygen, fluorine. Let's do another set of elements, the chlorine, fluorine, iodine, and bromine. You would recognize those as the halogens. Here we're comparing 4 elements in a group. And so if you have it already labeled, it makes it easy. The highest one is going to be up top. The lowest one is going to be on the bottom. So if we're putting it in order of lowest to highest, we would start with iodine, followed by bromine, then chlorine, and then fluorine. It's the easiest to remove an electron from iodine. It's the most difficult to remove an electron from fluorine. Well, what if all the elements aren't in the same period or group? You can still use the trends to figure out what order they would go in. The lowest one would be the one that's closest to the francium area, and the highest would be the one that's close to helium. So we would expect rubidium to be the lowest and beryllium to be the highest. So we go rubidium, next would be strontium, then magnesium, and then beryllium. We will talk a little bit about successive ionization energies. So successive means you have the first electron, and then how much energy does it take to remove the second and the third, and successive electrons after the first one. It always takes more energy to remove more electrons. So the first ionization energy will always be the lowest, followed by the second, and then the third. And after the valence electrons in an atom are removed, it requires a lot more energy to remove the core or the inner electrons. And so that is why, the main reason why, the core electrons are not involved in chemical reactions. And so here are the successive ionization energies for the elements, so lithium to sodium. And it lists the number of valence electrons in that atom. And so the first ionization energy is always going to be the lowest for all of these elements. Lithium has one valence electron, and so once that first electron is removed, the ionization energy for the second electron is incredibly high. So you see a sharp increase in the ionization energies when you go from the valence electrons to the core electrons. Beryllium has two valence electrons, and so the first ionization energy will be the lowest. The second ionization energy will be a little bit higher. And then when we go from removing the valence electrons to the core electrons, there's a sharp increase in the ionization energy. And you can see that in all of these elements. Once the valence electrons are removed, there's a sharp increase in the amount of energy it takes to remove an inner or core electron. And so there's going to be an ALEKS question about this, and what you want to do is you want to figure out which element is represented by the successive ionization energies shown in the diagram. And so each of these diagrams has ionization energy 1 through 5, so removing 1 electron to 5 electrons, and the amount of energy that it takes. And so you can essentially figure out how many valence electrons does the atom have looking at these bar graphs here. And so in all of these graphs, you're going to have lower bars, and then there's going to be a sudden jump up in the ionization energy for another electron. And so the small bars represent the valence electrons. And so in this left example here, this element easily loses 3 electrons. So that means that it has 3 valence electrons. In the question, it's also going to tell you what period that element is in. So you want to go to that period and figure out which element in that period has that number of valence electrons. So we'll go to period 3, and the element that has 3 valence electrons is going to be aluminum because it's in group 3A. And so that means that the element represented by this diagram is aluminum. In this next example, how many valence electrons do you think this atom has? Well, the values are relatively low up through IE4, and then there's a sharp increase to IE5. And so you would guess that this atom can easily lose 4 electrons, so it has 4 valence electrons. The question also tells us that it's in period 2, so we'll go to period 2 and find the element that has 4 valence electrons. So it's the one in group 4A, and that would be represented by carbon. Another trend is electron affinity. And if you've never heard the word affinity before, it's just a spontaneous or natural liking for something. So something that has high electron affinity really likes having electrons, and so it's going to attract electrons to it. If you've heard the word electronegativity before, electron affinity and electronegativity are very similar to one another. Something that has high electron affinity is also very electronegative. Electron affinity, however, is the energy change accompanying the addition of 1 mole of electrons to 1 mole of gaseous atoms or ions. So to sort of translate that a little bit, if you add electrons to an atom, is it going to benefit the atom energetically? If it releases energy, that's favorable. If the atom has to use energy in order to keep those electrons nearby, that's not going to be very energetically favorable. And so those atoms would be said to have low electron affinity. And so the trends are a little bit difficult for this property because it sort of depends on which element you're talking about. But in general, your reactive nonmetals, so think of things like oxygen and phosphorus and fluorine, those are going to tend to form anions. And that's because they don't like to lose electrons because of their high ionization energy. But they also attract electrons strongly because they have a high electron affinity. And so when an atom like fluorine gains an electron, it releases energy. And that's because it's obtaining the noble gas configuration. So because it loses energy, that is said to be a high electron affinity, and it's going to attract electrons strongly. So to summarize that, reactive nonmetals have high electron affinity. They tend to form anions because of that. Your reactive metals, tend to form cations. So think of your elements like sodium and magnesium. The reason they do that is because they have a low ionization energy. It doesn't require a lot of energy to lose an electron. And the reason that they do not form anions is because they attract electrons weakly. And then noble gases, they don't form ions at all. Not cations, not anions. And that's because they have a very high ionization energy. It requires a lot of energy to pull an electron off, so it's not going to form a cation. And they also have very low electron affinity. In fact, it requires energy, in I think all cases for the noble gases, to hold an extra electron nearby. So they do not attract electrons at all. And so there's not a nice, neat trend for the electron affinity with the periodic table. Again, I think it's much easier to remember that the nonmetals, so this little summary up here, nonmetals have high electron affinity. They attract electrons strongly, and that's why they form anions. Metals have very low electron affinity. You see these lower negative numbers. They do not attract electrons very strongly, so they tend not to form anions. And then noble gases actually generally have positive values, meaning it requires energy for those atoms to attract an electron. So they will not form anions at all. The final property we're going to talk about is metallic behavior. So what makes something metallic? Well, if you think about a metal and the properties of a metal, those are essentially what you should be thinking of. In a lot of cases, they're shiny solids. Not all of them are, but many of them are. They tend to have moderately high melting points and boiling points, and as a result are solids at room temperature. They're good conductors of heat and electricity for the most part. They generally tend to be easily malleable. But one of the most important properties about metals is that they lose electrons to form cations. So we already know that about metals. They tend to give away their electrons to form cations. And another way of saying that is that they're easily oxidized. And so remember, oxidation is loss of electrons. And so a metal, if it can easily give away its electrons, means it's easily oxidized. And so the trend in metallic behavior is essentially the same trend as atomic size. And so helium is the least metallic element. Frank down here is the most metallic element. So as you go down a group, metallic property increases. As you go across a period, it decreases. And it's easy to use the periodic table to remember those properties. If you take group 5, for example, at the top we start with nonmetals, and at the bottom we end up with metals. So we can very clearly see that we are increasing in metallic behavior as we go from a nonmetal to a metal. And so a summary of the 4 properties we talked about and their trends are in these graphs here. Atomic size and metallic behavior have similar trends. Ionization energy and electron affinity have similar trends. Just remember that the noble gases are omitted from the trends for electron affinity because they don't fit the increasing as it goes across. Note that there are many exceptions to the electron affinity, and I tried to summarize those for you. But make sure you're generally familiar with these trends, and you could predict or maybe arrange elements in a certain order based on any one of these properties. And also be sure that you're familiar with what each of these properties is and what it says about the atom's behavior. And so that is the conclusion of Chapter 8.